Hello and welcome back. In today's video, we are going to take another two-dimensional heat conduction problem, and it will be two-dimensional steady-state heat conduction in a square plate, like we did the last time. But in this, we have included uniform heat generation, which was not included in the last time in the last video. So we will be having a rectangular plate here, and all of its boundaries are kept at 0 degrees Celsius, and the whole domain is generating heat at a rate of 10 to the power 5 watt per meter cube, and we have to find temperature at this middle location x comma y. At this location we have to find, so that means we have to find T at here. In the problem it is 1 meter and this height is also 1 meter, so we have to find temperature at the location of 1 by 2 comma 1 by 2. Thermal conductivity is given 10, and boundary conditions we have specified 0 degrees Celsius. Now we know that the general heat conduction last time was the Laplacian of T equal to 0 because there was no heat generation. This time the Laplacian of T is equal to minus Q divided by K. This is the general heat conduction equation for today's problem. We have uniform heat generation as well. Now when we solve this we solve this differential equation, and we get the solution in this type of this form, which was which is like the last time. Last time the equation was in the infinite series form, and right now it is also in the infinite series form. So we have to solve this infinite series equation to get our value of t x comma y at 1 by 2 comma 1 by 2. So this solution consists of two parts, this prefactor and this infinite series. First we'll deal with the infinite series part. So infinite series of this numerator and this denominator. First we'll start with the numerator. We know if when we put L is equal to, L is basically here Lx, Ly, both are 1 divided by 2 meters. So when we put L is equal to 1 divided by 2, x is the location, which is x coordinate is 1 by 2 here as well, and y coordinate is 1 by 2. What we get here is overall sine of m pi by 2, and we get sine of n pi divided by 2. So what we have here is our numerator is now m times pi by 2, and we can see n and m both are odd, always odd, and sine of odd multiples of pi by 2 is either plus 1 or minus 1, because for example we will take one example from odd. Pi by 2 is, for example, 1 times pi by 2, that is 1, and 3 times pi by 2 is minus 1, so they alternatively change their signs. So one thing is clear, their value are going to come either plus 1 or minus 1. So there are two signs in multiplication. So when both will be 1, so multiplication will be 1. When both are minus 1, multiplication will again be plus 1. So we know the numerator is always 1. That's why I have written this here. So the numerator is always 1. Now the denominator, what we are left with here is we are left with this summation of 1 divided by mn, m square plus n square. This is a this is a general infinite series which we know, where we solve them, where m and n take only the odd values, and this series goes to infinite. Its value is 0.448 value. So we got the two terms. Then there is prefactor. This is the infinite series, and there is a prefactor which is actually on the previous page. Here we have the prefactor term in the 16. We have this prefactor term 16q L square divided by k pi power 4. So now pi power 4 is 97.409, and when we do 16 divided by pi power 4, it comes out to be equal to this. And then there is q L square term divided by k. Now q is 10 to the power 5 from the problem. L is 1, which is the length, which is either Lx or Ly, both are L. So L square, which is 1 square, and divided by k. and k here is 10 from the problem given. So we get this term 10 to the power 4. I'm taking big jumps. I'm not solving this in detail because our goal is the COMSOL solution. Now, when we combine all of the terms in um, which are in multiplication with each other, first of all, there is k pi power 4 term. There is, sorry, 16 pi power 4 we evaluated separately. Then q l square by k we evaluated separately. Then we evaluated this term separately. We got three terms, and those three terms are these. This is the first term, this is the second term, 16 divided by pi power 4, and this is our third term. They are in multiplication with each other. So when we multiply these three terms like this, we get 736. So our center line temperature is 736 degrees Celsius for this problem. Now we'll solve the same problem using COMSOL multiphysics and compare the two solutions. So what we will do is we'll open the model wizard. Since it's a 2D plate, so 2D geometry, heat transfer in solids. This is our module that we are learning. Now we have added the module. Now we'll choose the study, which is stationary, because there is nothing to do with the time, so it is stationary steady state. Now first of all, we have to create the rectangle. So we'll go to geometry, we'll right click, then choose rectangle. Then we have to choose length, width 1 meter, height 1 meter, which that is by default chosen, and we'll build it. Now this is a rectangle. Now one more thing we will build is a point at the center, because that will help us to evaluate the temperature at that point. So our point is at 0.5 comma 0.5 coordinate. So we'll build. So we have a point at the center as well. So we are done with the geometry. The next step is to assign the material. So we need only one property, that's k. So no need to assign the material. We will define that property. We can define that property in the physics itself. We will go to solid, and we have k rho cp, and we will choose user defined k and give it value 10 according to our problem, and units are in the SI unit already. So we'll go to initial value, and we can keep this 20-degree initial value, doesn't matter. Then we have to choose the boundary conditions. All the four edges are at 0 degrees Celsius, so we'll choose temperature, and we will write 0 degrees Celsius, and we will choose where this, as well as this is the one boundary condition. Another thing, it is heat is being generated in the entire plate, so we'll choose heat source. It's a heat source itself. So general heat source in watt per meter cube, which is according to our problem given as 10 raised to the power 5. So this is according to our problem, and we have to apply it to the entire domain. So we applied it to entire domain. So we are done with the boundary conditions. Now we'll go to mesh, and we will discretize our domain, and we'll go to study stationary, and we'll compute it. So when we compute it, we get our solution here in the form of surface plot, and we shows us how temperature varies from center to the edges, because edges are kept at 0 degrees Celsius and the heat is being generated inside the blade. This is the temperature distribution that we can see, and we can show units as well. So the temperature varies from around 0, which are at the edges, up to more than 700 degrees Celsius, which is at the center, and our point is at the center. So we are expecting our temperature to be in 700s, that we also saw in the theory in the analytical part. So we'll go to derived values. We have to evaluate temperature at a point, so point evaluation. We will choose that point that we had made earlier, this point, when we select it, it will appear here. So when I take cursor there, it shows this 3 over here. So this 3 should appear in here, meaning we have selected it, and we'll choose unit as degrees Celsius, meaning we are telling it to give us temperature at the center in degrees Celsius unit. When we hit evaluate, we get the temperature here 736.7, which is around 736 degrees Celsius. When we compare it with our uh, analytical value, we can see that analytical value is over here. It is 736 degrees Celsius. Clearly it is 736 degrees Celsius, and it is matching with our value, and it's exactly matching with our value. So this was the analytical solution and the COMSOL solution, and both were in exact agreement with each other. So this is how we solve 2D plate with heat generation using COMSOL multiphysics. Thank you.